All right, so let's talk about artificial neural networks, which we've been using. And these are a simplified cartoonish imitation of what's known about neuroscience and the way our brain works. And this is what all the big AIs use. So we'll talk about biological neurons and the perceptron, which have been around for a long time. They were talking about this when I was doing computer models of brain function from a medical point of view a few decades ago. And we'll talk about how these things work. Turns out perceptrons are quite limited, but multi-layer perceptrons get a lot better, and that's what we're using in many cases. So it's been around for a very long time, artificial neural networks since the 40s, but they didn't really work very well until the 90s when we started getting, they come every few decades, there's a wave of interest, and people think they're actually going to do something valuable, and then it dies down as it turns out that the equipment available at that point is not useful. And now we're living through the biggest wave where they're actually doing a lot of useful things. And that's partly because we have a lot of data now because of the internet. And the training algorithms has improved, as we're going to see. And it's turned out that you don't have to worry so much about it falling into a local minimum and not being able to find the global minimum in parameter space. That turned out to be less of a problem than people expected. So right now, we're in a giant cycle of funding and progress, huge amounts of money going into neural network design. So they imitate biological neurons. And so a biological neuron has a nerve cell and it has a whole bunch of dendrites here, which reach out and touch neighboring nerve cells. So it combines the input from a bunch of nearby nerve cells. They go into the nucleus here, and that sends one signal out the axon. So they have many inputs and one output, which goes to the next layer. And that's the idea. And so they have action potentials and neurotransmitters and synapses. Synapses are the junctions. And the details of the biological one are not really that important to us because we're making artificial neural networks, which only resemble this in a sort of broad overview. But here's how it looks. This is a real sample of the human brain. You have this tangle of neurons, and then they send the signal along to some other layer of processing. And that's the idea. And the network of many neurons working together accomplishes something like vision and consciousness and behavior. So the logical computations with neurons, you have some inputs at the bottom and some outputs at the top. And so you can have neurons that are just on and off. So if you have, here we are, C equals A. This feeds into that one. And if this one is on, the next one will turn on. Here you have A intersect B, where both of these have to be on in order for that one to turn on. Here you have A not intersect B, and A or B. So each one has to have two positive inputs to make a positive output here. And so you have two positive inputs from each of these. So if either one of them is on, this one will be turned on. And here you have not. So it's going to be A and not B. So these have two inputs coming in and a negative input from here. So it's only going to be positive here if A is positive and B is negative. That's the idea. That's how you could simulate digital computing, ordinary digital computing with transistors with neurons. And the perceptron works this way. It's been around since the 50s. So you have, it computes a linear function of all the inputs, these weight factors times the inputs, and then it applies a step function to it. If the final output is above a 0, then you have 1. If it's below 0, you have 0. So the answer is just 0 or 1. One threshold logic unit, therefore, can only perform a binary classification. It can only tell you yes or no on the output. It takes a lot of inputs, but it ends up with a step function, so the output is just yes or no. And you train it just to adjust all these inputs. Each of these has a weight and a bias, which is the slope and intercept of the linear dependence on all these inputs. And so that's a perceptron.
So my answer was to be how that's.
I think that's not intended for us. All right. Anyway, so the layer of threshold logic units, you catch every one of these connected to every input. They have different parameters here, and that's a fully connected layer. So this is the output layer. So you feed in some inputs, and you get a series of binary outputs here that are essentially 1 bit each. All right, so this one can make three classes. Each one of these can be true or false. So one of them might be true, and then you'd have that would be the result. So to train these things, the idea is, I remember hearing this word a lot. If one neuron triggers another often, the connection between them gets stronger. And all right, so you can train a perceptron. You calculate this. The connection weight is the W's. X is the input value here. Y is the output of the neuron. Y is the target output of the other neuron. And so this is the measure of error. You have the observed input, and this is the target output that you want to train it. And eta is the learning rate. So you adjust the weights in a direction that will minimize the error, and you have a learning rate where you take the error and multiply it by this. And so that's the simple plan. Now, the perceptron cannot compute XOR. It's linear on all inputs, so you can't have a situation where when both inputs get larger, the output gets smaller, which is what happens for an XOR operation. So it's really very limited, but you can do it with 2 layers. So here, if you put in all weights of 1, and here's the bias, minus 3/2 and minus 1/2. So here you have an input of 2 minus 3/2. That will be a positive 1/2. So that will propagate to here and turn into minus 1/2. And this minus 1/2 will turn it into minus 1. You feed 2 into here, minus 1/2 is 3/2. That will go here. And so this will have the end result. And I could go through these one by one, but I think it's not really that important. The fundamental point is you can do an XOR with 2 layers. All right. And so a multi-layer perceptron is essentially what modern neural nets are using, although they don't use as simple a function as a step function here, which we'll get to. So this is a feed-forward neural network. You feed in the input, it goes to a hidden layer of neurons, and they go to an output layer, and the information propagates in only one way. You don't have any feedback. And if you have a deep stack of hidden layers, then you call it a deep neural network, where it goes through several layers of hidden processing. And this, in 1970, they developed the essential trick of reverse mode autodiff. And this uses differentiation in all the parameters, partial derivatives, to figure out what direction in parameter space will lower the error. And this is what's called backpropagation or backprop. So what you do is you initialize all weights randomly, then you choose a mini batch of instances of your training data, run it through the network to the end, measure the error, and then analytically compute how much that error depends on all these weights. So you can figure out what direction will lower the error and take a step in that direction. Now, your activation function should not be a simple step, or you won't have any slope to go down. It'll just be on or off. So you replace it with a smoother function like one of these. ReLU is very common. Rectified linear, the purple one, where you have it start at 0, and then instead of jumping up to 1, it just linearly rises from that point on. That way, and then you have the complete smooth ones like sigmoid and hyperbolic tangent, which give you a nice smooth area. They all amount to about the same thing in practice. You have to have some kind of slope here so you can move down the slope. All right. And okay, so you can predict a single value. If you just want one number, like whether something is true or false, you have an output layer here, a hidden layer, and an input layer. If you want to predict a 2-dimensional value, then you can have 2 outputs, which would be X and Y predicted, to try to find, say, the center of an object in an image. And so you have to have activation functions at the output neuron. If you want a varying value, smoothly varying, you leave the output unchanged. It'll be a weight factor, an activation number. If you want to guarantee a positive value, you can use ReLU, which is 0 and then has linear growth, or you can use one called Soft Plus, which smooths it. If you want to restrict the range to some other value, you can use sigmoid or tan-H. And so your error measure, typically the mean squared error, this is the classic one. If you have a lot of large outliers, though, then the squaring, which makes large outliers more important than smaller outlying outliers, you might want to use absolute error or the Huber loss, which combines both. And we talked about this before. This is the L2 measure and the L1 measure because it uses the square of the error or the first power of the error as a sum, as a measure of quality. And so now here's what you have. You have hyperparameters. This is typical. Here's the various hyperparameters you can use to control the output of your neuron. So there's a number of hidden layers, typically 1 to 5, number of neurons, typically 10 to 100 per layer, one output layer per prediction dimension. The most common activation in the hidden layers is that rectified linear. So it's just 0 for small outputs and grows linearly above that. The output activation can be none or any of these, depending on what you're trying to get. And your loss function can use the mean squared error or some combination of linear and mean squared errors. So here's classification. For binary classification, you have one output layer and a sigmoid activation function. The output will a smoothly varying value between 0 and 1, so the output will be the probability that this one is positive. For multi-label classification, you have 2 of these, and these would be the probability that it is in one category and the probability that it's in another, like the probability this email is spam and the probability that it's urgent. For multi-label, you'd have softmax for each of these, so the total probability of all of these would be 1, and this is what we had in that project where we were sorting images into 10 categories. You'd have a probability that's in each of the category that adds up to a total of 1. And that's how it works, the mathematics for it, just to normalize it in a way that the total sum is 1. All right, so here's an example, same kind of thing here, talking about the various output layer activations, the number of hidden neurons, and so on. Another thing you can do to define the cost for multi-label classification is a way to count the erroneous predictions and get a measure of loss that is larger as the erroneous predictions are larger. So they use this function to do that. And the details of exactly how you measure it don't really matter as long as you have some kind of function that gets bigger when you're making more mistakes. So you can implement these things in Python with the Keras library, which we've done using the Fashion MNIST library of images of clothing. And we loaded the data set here with TensorFlow, and you train it on 5,000 images. You divide by 255 to normalize the brightness values before you start. This is, as we talked about many times, if you don't adjust the scale of the input, you're going to get a biased result that weights some portion of the input far more than others. So here's the model. Sequential means we're going to have a stack of layers with information flowing in only one direction. We flatten it to convert the 28 by 28 array to a one-dimensional list of 784 values, which is how it works, but it is kind of strange that you would just treat each of the pixels as totally independent bits of data when in fact they aren't. You have lines that are thick and you have borders that are thick to where the pixels actually contain similar information in neighboring pixels, and you have destroyed all information about the geometric location of the pixels here. So this is kind of unrealistic, but that's what we actually use. Then you have dense layers. This will make a hidden layer and another hidden layer using the rectified linear function. And then the output will be softmax, so it'll just have a probability that goes with a total of 1. So that's how and here's the number of neurons in each layer, which you can adjust. So that's what you have here. The input image is a square. You flatten it out into just a bunch of pixels, which you treat as independent pieces of data. Then you go through some hidden layers, and your output is normalized so that the total output of all the categories is 1. And so here's how the model looks. You have your input layer. You have no parameters here because it's just flattening out the input. Then a dense layer of 300. You got this number, which I think is just 784 times 300 plus 1. And then you have 300 times 100 plus 1, and so on. This is how many parameters. So you end up with 266,000 parameters in your model. And cross entropy is the error message, is the error measure appropriate for a multi-label task. Stochastic gradient descent is what it's using to optimize it. And your metric is going to be accuracy, that with the thing you're going to report so you can see how well it's improving. So you just perform the fit with that information. And so here it shows you the number of mini batches The accuracy on the training set is here, and on the validation set is here. And you do epochs of training, and ultimately you generally end up being more accurate on the training set than the validation set, which means you have overfit to some extent. To some extent, you have fit the random errors in your training set, and that not all of that training applies to the validation set. So you have a learning curve. You consider how many epochs here, and what will happen to the loss. This is the accuracy going up and the loss going down. And as you can see, the I don't understand the difference between, validation. Okay, so the red is the training set performance, and the blue is the validation performance. So you can see it up to 6 epochs they match. After that, they start developing a difference. So although you are getting better performance, you're also getting a little more overfitting. And this may be what you see in the large language models, I mentioned before. Large language models are very good at answering your questions, but they also clearly have some degree of overfitting, overtraining, because if you give them a page of a real novel, they'll report exact other pages from that novel. All right, so you have hyperparameters. One is learning rate, and then there are a number of layers, neurons per layer, an activation function. All those affect the training performance of the model. Now you can have more complicated models. Here's wide and deep. You can have deep patterns, which are what we talked about before, where the input passes through all these layers, but you can also have simple rules in the wide path where you don't bother doing the hidden layers. You just go straight from the input to the output, so you can have very simple rules, like simple if-then. If this pixel is on, call it a 1. If this pixel is off, call it a 0, that sort of thing. You might have some portions of the image that are so important that you don't need to do this intermediate calculation. And that creates a more complicated model where the data is used in 2 ways. And so you can create them here. Normalization standardizes the input. Then you have hidden layers operating as usual. And the concatenation layer combines this into one tensor, and the output layer is there. And if you want to put them in order, here's how you do the input and the deep learning. You use concat to combine the normalized layer with the hidden layer. So here, you calculate the normalized stuff here and pass it to hidden 1, and then you take hidden 1 and pass it to hidden 2. So this process, this parameter includes the data that you went through the deep model, but you also add the normalized here at the output layer, which skipped the hidden layers. So you have some data that passes through the hidden layer, and you also have a path for data to pass past the hidden layers, and that's a wide and deep model. And then you adjust all the parameters to decide how many of the pixels should go one way and how many should go the other way. Right, and you can have multiple inputs. You can have some input that goes the wide way and some that goes the deep way, and sort them out also in the model. And it will just optimize all these parameters. It doesn't really matter what the shape of the network is. It's going to use the same logic to optimize the parameters. So you might use multiple outputs if you really need 2 things, like you're going to locate a picture, the object in a picture, and then you're also going to identify that object. So that's regression and classification, and you can have multiple activities going on in your network. You have a complicated network like this. And you could consider solving those with separate networks, one to locate the object and one to identify the object. But if you combine them into one network, then it might be able to mix those 2 tasks together in a way that improves performance. Then there's regularization, which is adjusting this to smooth things out. So you can have the auxiliary output here to ensure that it learns something useful. I'm not quite sure about that. I'm not going to worry about that right now. So you have multiple outputs where each output needs its own loss function, and you need labels for each output. You can also add things like for loops and if statements. You can make these models as complicated as you want to. And there is a visualization product called TensorBoard that lets you see these learning curves and play with them and view statistics and such to show how well your model is learning. So to fine-tune these models, here's hyperparameters you add in, number of layers, neurons, activation functions, learning rate, batch size, and so on. And you can tune all of those by trying random values until it finds a good fit. This is included in the library we're using. And there are also techniques like stochastic gradient descent and ADAM that can do this. This is like stochastic gradient descent, but it doesn't have a fixed learning rate. It starts with a large learning rate and then slows down the learning rate as it approaches the bottom to make it converge more rapidly. So your number of hidden layers, in principle, one hidden layer can do anything, but for complex problems, you get more value out of multiple layers. And this is considered to be true of the human brain. The human brain has a retina at the front to pick up images where you just have one pixel per refers to a certain area of the image. And then you have layers of processing that detect edges and objects and motion and direction of motion. And then you pass those higher level parameters to higher levels of processing. This turns out to be the most efficient way to do it in the human brain and often in artificial neural nets too. So at the higher level, you'll have edges and motion detected. And at a really high level, you'll have a neuron that just picks up a face. And they've done this biologically with the human brain. You can have a celebrity like Brad Pitt, and people will have one neuron in their brain that fires when they see Brad Pitt. So humans have evolved their brain to recognize and identify faces efficiently, which makes sense because faces are important for survival. So you can start a new model from a pre-trained lower level. So you, for example, you have some kind of image classification or speech recognition task, and you don't bother training the whole thing from scratch. You assume that the lower levels are just determining general features, and you can move them along and include the pre-trained one. So you don't have to train all the levels. You just train the higher levels on your specific task. So you have the input and output are defined by the problem. And the old technique was operating in a pyramid shape. There was a belief that you should have more neurons at the low level and less neurons at the high level, which matches the sort of intuitive concept that first you're going to detect, say, the edges in the image, and there are less edges than pixel, and then you're going to detect whole objects, and there are less objects than edges, and so on. So intuitively, you would think you'd want smaller numbers of neurons in each layer, but it turns out that using the same number of neurons in each layer works better in practice. And that also implies that that intuitive idea of what's happening at the different layers is not really true. Sorry. So you can start with different paths. And this is like stretch pants. You start with more layers and then use regularization and simplify the model until it stops working and then backed off a little. This is a way to decide how many neurons to use in your model. And the most important hyperparameter we talked about before is learning rate. If you try to make the learning rate really fast, where it makes big jumps, then it will miss the minimum and wildly diverge and just go crazy on you. So one way to do this is train it at a very low learning rate, then keep increasing the training rate until it fails, and then back off to a fraction of that rate. That's a way to find the optimal learning rate. All right, and so there's other parameters out there like batch size. People have argued about how many instances to use at each cycle of training, which activation function, ReLU, is usually good. And the simplest thing, rather than trying to guess how many iterations to do, is just perform epochs of learning until the loss gets worse, and then you know you've hit the bottom. That's typically how you do it. So that's the conceptual ideas that are used in the learning models we've been running. And like I said earlier, people said, how's this working? And I said, well, we'll talk about it later. So this is more about what's really going on inside those neural nets. So I'm going to stop this recording.